for this, so it's on the record. Yes, yes. So I can share my screen with Zoom. All right, so your first programming assignment is up. I think you have access to it. August 31st today, yes. All right. So the idea of this is make sure everyone can open MATLAB, can use simple commands. And the question here is just programming the Gabler formula. So you use a Gabler formula for general programming, right? And then once your program is done, for a proof of concept to show me that your program works, you choose a robot and then you put information, input information to your program, and it should give you the correct degree of freedom using Gabler formula. So things that I'm looking for, things to include. You will give me usually the M file, the published file in PDF, and the output. So in your PDF published file, if you enter numbers as a user, your code will give you an output. Everything has to be meaningful. It shouldn't be like input 235, output 31. What does this mean? So at least degree of freedom is 2, right? Very simple. Things that it's important for me, and now is the time for you to go learn them, or if you already know, show me that you know, is checking for errors. So M, for example, has to be 3 and 6, right? So you can ask, we're talking about degree of freedom. So M was the number of maximum freedom in 2D and 3D. So if you're asking your user to give you that M, you should probably explain what M is, right? 2 for plan, M for planar, and for the spatial. If they are entering that, let's say a user said 4, I'm gonna put 4. It has to give me an error that 4 is not acceptable, right? Or you can say, you know what, let's take this out of the user's plan. Just ask them if it is planar or spatial. Whenever they give you which one, you'll assign either 3 or 6 to it. So you have a vector that reads that. Now, if you don't know how to do this, that's the time. This assignment is for you to brush up your coding skills. I added some resources for you to go through. Should be able to work with this. You can talk to each other, get help on how to use MATLAB, not doing the assignment together or copying from each other. You're also telling me, you're showing me your coding style. Nobody's gonna be from, I'm using camel case and this is my start, to going something very different or the other way around. So kind of I'm learning who codes which way. So when we get to our bigger coding assignment, it's easy for me to identify this is your work and who did what part of the coding. So if I group you with someone that doesn't know much and you know a lot about coding, and the final project or one of your bigger project comes in and is everything good, I'm going to talk to both of you, make sure both of you understood. Because if someone knows and you group with someone that is really good in MATLAB, you can't be like, I don't know, let this person do everything and get a point. No, it doesn't work like that. So checking for error, making sure you're getting an input from the user. Do you know what that means? Because I remember that we had problem with what does it mean? Who wants to volunteer and tell me what does it mean to get an input from the user? Yeah.
Like if you type something into the computer and then MATLAB, it's easy to type it in.
For example, yes. So you have a robot, right? You ask your user, for example, how many rotational joints does the robot have? And then they say 5. You save it somewhere, 5 are equal to 5, right? So usually we create a vector that's empty and then you start populating that and use that data to calculate, and output is the degree of freedom of the robot is equal to, and then you spit out the output. It should be meaningful. It should not require you to go line by line in your code to see what did you mean by this number. So if you haven't done this, that's a great chance right now to do it, because from the next programming assignment, I won't accept we don't know how to use MATLAB. Because one of the requirements of this class, of many that doesn't exist, is MATLAB, right? And it wasn't your syllabus. So I'm assuming you either had it, you saw it. The other thing is you could use MATLAB online. So if we do something in the class using MATLAB, you can just go online, MATLAB online, use your Ohio State user password, and everyone have access. So I don't have a computer. is not a good excuse because you have a phone, you have a lab, and you have an iPad. So not everyone has iPad, but you have access to a computer in the lab, right? So from my point of view, everyone has access to a computer that can connect to MATLAB. Sounds good? All right, so you have time to submit this. It's here until September 7th next week. So if you have questions, come to my office hours. I have 3 office hours, right? And you can also ask me before class, not after, because I have to leave. This is a rubric to tells you like how what am I looking for? So don't just look at the rubric and say, okay, item number 1, she wants this, make sure it has it. No, do your code, make sure it works the way that you understood, and then go to the rubric and make sure it checks all the boxes. All right. Any questions? No, clear about that? I tried to explain everything very well, and I want you to use the publish feature of MATLAB. How many of you use that? Raise your hand. If you were in my control class, you had to do it. If not, I think I have, yes, I shared how to publish. So you have to get a very nice PDF that has basically a list of all the section you create, and then everything is very neat and looks like a report. All right, so if you haven't done, familiarize yourself. So this is your code, this will be your published version. So this is what I want. So you can open a Word file and copy paste what you get from the command window. You cannot snapshot things and put in Word and convert to PDF. None of them are acceptable. So this is really to show you what are my standards and what I expect. All right. Now let's go to the course, to today's lecture. Need to see this. All right, so I'm assuming that you will go and check CP2 solution. We already did. I still have to solve that one last additional example I gave you. How many of you tried to solve it? All right, I'll post the solution. So I'm going to give you a little bit more time to use that as your practice example. All right, and then either on Friday or Monday as you catch up, I'll go over that. This is another practice problem for you. This is in 3D. You haven't done 3D yet, right? So, but you have the table, you should be able to do that. Remember what was important when you were analyzing the degree of freedom? What are the things you would look for? Yes. Links and joints, right? So if you look at here, so this is showing, so this is what you get, like if you get a schematic. So introducing to you that these are S joints, looks like this. Your R joints are gonna look like that. So you'll have to identify. Now you see that there's RSS, RSS, and then there's 1, 2, 3 sides that look the same. So these are kind of like a block. So if you figure out this block, then this leg and this leg are the same. You'll see that the degree of freedom of this is more than what you expect. Now, if you look at this top plate, that's one link, right? And then you have R connected to it. And then this is link. And then this one, you don't see it, but it's the same as these two. Like there's another link up there. So my suggestion would be maybe separate these and then look at it and then solve. And this is your base. So this will be connected to something else, but you're going to assume to the ground. So this will be your ground link. So you say base or ground. So try to solve this one and the previous one, then hopefully on Friday, and if not on Monday, I go over all of them. I want you to have the opportunity to study and try to solve it. Any questions on that? Pretty clear. All right. Rigid body transformation. We talked a little bit about transformation. How many transformation could we have? Did we talk about, or you know of, what is transformation? Nathan? Do you remember? Yes. What did we talk last class? Frame to the other frame, right? So from one frame to the other frame, we want to look at our object to see how it changed. Now, sometimes there might not be any change, appear change, so we have transformation in one. It's 1 to 1. There is still transformation, but it's 1 to 1, nothing changed. It just tells you nothing changed. Now, the kind of transformation, they're either rotation or translation. Why? Because if you remember, we have 3 axes in orthogonal, so we are in Cartesian in board, right? So from that class, we are in Cartesian. So we have 3 orthogonal axes, so 3 translation, and then 3 rotation around each of them, correct? So these are all the transformation we can have. We can have all of them, combination of all, or 1 or 2 of them. So let's say that this is your object. You're gonna put every object will have its own reference frame, right? You can call it body frame. And that object, if it is my hand and there is a reference frame attached to my hand, if I rotate my hand, the frame rotated too. So if I want to know what happened between these 2 scenarios, I have to look at the reference frame. How do they change with respect to each other? There's only rotation, so the transformation here is just rotation. Now, if I rotate my hand and move along one of the axes, rotation and translation happen. So think about the screwdriver. We talked about it. Screw. When you screw a screw, you have a rotation, and also there is a translation. Now, this is called screw motion. It happens so much in our application that we created a new transformation, but it is combination of a rotation and translation. We're gonna call it screw motion. There's also wrench, because wrench is also a rotation that can cause also a translation. So we have a transformation called wrench. So if you are reading your book, you're gonna come across these 2. And that's just basically combination of 2 a rotation with 2 transformation, and you're going to talk about them when we get there. Your book it's kind of from a bigger overview, top view starts. I start from retail, like build back up. All right, so at the end of the chapter, we get to the same place. And your book has a lot more mathematics in it. I don't think it's necessary at the beginning. You will get to all of them, don't worry about it. I won't miss any math. So, if this object A rotated and then, so let's say from here, it went here, you can say this was a translation, right? So along X and Y, and then there's also a rotation that is happening here. So you see that it doesn't matter if you rotate first and translate later, or if you translate and rotate. When you're dealing with orthogonal systems, we can, it is commutative. You can rotate, translate, or translate, rotate. The final answer should be the same. So you don't have to worry about which one do I do first. You should be able to identify which one is happening. All right. This is the screw motion that I mentioned. So if you think about from point S, this one is rotated to that, so it's in a screw motion. And then from here, this object rotated up and also translated here, right? So there's a rotation and translation. Right now, we're just trying to identify them. You're gonna calculate each of them separately later. It is important for you to be able to identify which one of those 2 happened. All right. So some definition, it's good to be familiar with, so we all have similar terminology. So a rigid body, we're talking about in 3 dimensions. So when we are in 3 dimensions, something can happen on the surface, 2 dimensions, a subset of 3 dimensions. So I'm talking about the higher dimension, but it applies to 2 and 1. So in R3, Whenever we don't have any deformation or it's very negligible, so we have rigid body. This becomes our assumption. Everything we talk about is 3D and it's a rigid body. There's no deformation. We can define transformation as a single body mapping from one reference frame to other. Finding what this map is basically what is the transformation. Now, when we map, if our body is a rigid body, every single point, when we have the mapping matrix, every single point will be mapped through that one matrix to the destination, right? Because we don't have deformation. That's why we usually put the reference frame at the center of the mass of the object and say, if we can find the transformation from the center of mass, where does it go? It applies for everywhere else in the object. Usually, you show them with 1 point, right? That was one of the discussion we had last week. Because of assumption, the rigid body assumption. So if you're not told, put the reference frame on the center of your object. So if I have an object, let's say this, I'm gonna say this is gonna be my P point, right? And then I'm going to transform it to another frame, P prime. This is G. If I know what G is, then I know every single point on that object that I call P, which is the new reference frame. Now, how about vectors? So these were about points, right? What happens to the vectors? If I want to transform one vector from one reference frame to another, what will happen? How do we define it based on what we just talked about? Let me draw maybe a vector for you so you can. So let's say in that same plane object, I have Q and P, and this is my vector, right? V is P minus Q or Q minus P. How do I map this? Someone else. You can answer it wrong as the first one. What is a vector? Yes. Yeah, you're still mapping 2 points. It's a rigid body, they belong to that object, right? So they should not be deformed or anything. So you can translate all the properties using P. So still you can use G. You are basically sending Q to Q prime, P to P prime, and since it's not deforming, then you have your vector. So we can also, using the same transformation, transfer vectors. So position and velocity can be transformed from one frame to another. Position is a point, velocity is a vector. Does that make sense? Because when we are talking about state of an object, like in 20 seconds, where does this car go? Right? You have the position of the car and velocity of the car, and then you're going to decide. You need to, and then you're going to say that, how about from the point of view of the camera? It's like, okay, I'm going to just look at the velocity vector and the position point from that perspective. So correct. This becomes Q prime, P prime. So V prime becomes P prime minus Q prime. So you're still using G as your transformation. So the solution always becomes how did one reference frame transfer to another reference frame? Why? Once you have this mapping, once you have this mapping, everything can be transferred. Now, this is only correct if we have rotation. Now, if we have translation, you're changing the center of the reference frame a little bit as well. So we can say about the vector, if it is rotation, you can use the same method. But when we have translation, we won't say for sure it's the same method, depending on what our translation. Right? So if rotation, let's say this was G prime, G is G prime. If translation plus rotation, then G is not always G prime. And you will see why. We will have a 4x4 matrix, and then from mathematics, you can also tell why it won't work always like that. But if you have rotation, it will always be the same. Yes. So I'm introducing this vector to the G prime mapping of the G prime. So instead of calling it G, I'm calling this G prime. If you are moving a vector using a mapping to another reference frame, right? If these two reference frames only have rotation in them, G and G prime moving a point and moving a vector will be similar. But if your G prime is here, when you're moving a vector, there is a little bit of transformation happening because let's say this goes up or it moves in a direction that impacts the direction of your velocity, then the angles won't be the same. The values are the same, but the angles are not the same. Then you can't say they're the same. We will dive into all of this. This is just basic definition to prime you. So if you heard them back, you come back to this slide. Some properties. We have rigid body, so the length also are always preserved, right? If a car is 1 meter, 2 meter, it's always 2 meter. It doesn't matter how many times it goes through transformation. Meaning that if you look from a camera at a car and measure its length, should be the same as if you look from an observer's reference frame. It's still the same length. That's basically what the person is. Orientation is also preserved. So if the front of the car built a 35-degree angle with an antenna, it doesn't matter which reference frame you're looking, that angle is always the same. So the body, the properties of your object would not change with respect to different frames. That's basically what those two are saying. So that's the preservation for the length. So the norm of the 2 points that you choose on the object will be the same values. And here, the cross product of the vector, if you cross product and map them, will be the same as if you map them separately, then get a cross product. So this is the mathematical description, and the simple description is what I just talked about. All right. This becomes handy because people use these when we are actually doing matrices, but what does it mean is really important. Any question on that? These are basically reviews, yes. Here you see that they're the same mapping, right? Yeah, you can say that. This is just a notation. Yeah. Just showing you distinction between like it's just like a notation. You can say you can call your mapping to be F, to be G, to be W, whatever it is.
Is that not a specific sort of characterization for this specifically about you have regular, that's like general.
General transformation. Yeah.
G, how does G have it?
For now, they don't differ. They don't differ because we don't know what they are. When we go further, we will identify them what if there was a difference. So assume this was G. Stevenson, we're talking still about general transformation because we don't know what they are. All right. This means that if you have vector V and vector W, get the cross product of them and apply the transformation, you will end up with the same thing as if you map V first vector, map the second vector, and get the cross product, they will be the same. That's what it says. why we relate orientation to cross product? Remember, the magnitude was the parallelogram, the orientation was the orthogonal. It will tell you. So when we talk about orientation, we talk about the cross product. Because it's a vector, so it has that direction. Thank you. All right. We get into exciting stuff. Did I miss something? No. So the inner product is also preserved. The angle between two vectors stays the same. Why do we connect the angle between two vectors to the dot product? Then you remember what is V dot W? Magnitude of V times magnitude of V times sine of theta, right? So, and then cross product is preserved, they're orthogonal, we just talked about that. If they're orthogonal, they stay orthogonal, because that's what cross product does. Now, if you look at this, so this is a reference frame, there is a cube. We are rotating this cube from this original point to this new point, to this new, place. You need to take a look where P was. So you are basically mapping this point P using this G transformation. We have ways to find out what this G is. Once we have that, we can find every single point of that box. And so sometimes we move the reference frame with respect to each other. Sometimes we rotate the object in the reference frame. So if you imagine there was a body reference frame here, that reference frame is now rotated with respect to the original. All right. So how many transformations do you see here? So let's say that we start from a fixed frame. Usually we either call it is fixed frame right in the corner of the room. In this example, so this is basically showing you the ground. So this means, let me write it better, fixed frame. Usually corner of the room or ground floor, somewhere that you know what is exactly the, where are we measuring everything. We usually call it S frame or fixed frame, and then we measure everything else with respect to it. Sometimes we call our first frame or that as frame 0 or our initial frame. So these are all conventions. We want to stick to this convention. So if you said S frame, I know what you mean. Or if I say frame 0 is here, you know that that's the initial frame. Everything from now will be compared to this initial frame. Okay, so we're going to stick to the terminology and then we show it as this. So I say frame. This is S. Then I can call it S frame. And if this is your object, we usually call it body. So body frame. This is frame B. You see that the subscript is B, here the subscript is S. And usually we call this body frame, especially if it is attached to the object of interest that we are tracking. Okay? So if I told you what's the body frame orientation, I'm talking about the frame that is our main object. And we're trying to figure that out. All right. Now, look at the orientation of your fixed frame. Z is pointing up, X closest to Y, right? So first of all, we are following right-hand rule. So here. Now look at the orientation of that one. So this was that, and then that one is here. So it's kind of a little bit tilted, right? Now, comparing these two, what kind of transformation happened there? So that object was in the center of your fixed frame. It was here. Now it moved. You close your eyes for 5 seconds, you open, it's like a cat. Jump. So what happened? Right. It rotated for sure, right? Because from being here is now tilted. What else? Translated, right? So how do we know? So what is the translation? Can you tell me? P, right? So we see that all we care is the center or origin of that reference frame and the origin of this reference frame. So we put our reference frame at the origin. So we are measuring how far or how that origin translated. So P vector. Now we know P is the translation. Should not write in red. So translation P happened and rotation happened here. Now this P translation could be in all 3 axes, X, Y, Z. It could be just along X or Y. Here is probably around about all 3 of them, but I don't know. We need to know where exactly that position is. So we measure, we say that the origin of that point in frame in our original frame, because we know where this is. This is 0, 0, 0, right? And then we want to know what P is. So to show P, so let's say we are talking about the position of this new object. The position P is measured in frame S. The rotation will also be measured there. The orientation, when we say orientation, we mean the rotation that happened. We're gonna show it with this transcript. So X, Y, Z, because rotation happens around those 3 axes, right? In frame S, our original frame, and then which frame you're trying to measure the orientation, the new frame B. So basically rotation about X axis in the original frame, right? We're trying to measure the new frame. So this is our new frame B, and this is our original frame. We find the rotation of X, Y, and Z. Basically, we're trying to understand how much, like the degree, the angle. This X-axis rotated about this X-axis. Like, what is the angle? Once we find that, we do the same thing for Y and Z, then we know how much each of those rotated. That becomes the rotation part of it. The translation, we get the origin and say where you are with respect to that point. That becomes a translation. From here, we create our transformation. So this rotation becomes a rotation matrix. So that orientation, like right now, is software like a vector, right? And you want to know how much X is rotated about all those 3 axes. So 3, 3, 3, and 3, 3, 3, 3, 3, like 3 by 3 matrix. That's why we call it rotation matrix. The dimension will be 3 by 3. So this rotation matrix describes the rotation of the frame B. Frame B axis with respect to frame S, which is also called fixed frame. So translation is usually about along XYZ, or rotation is along those axes. Let's solve a problem so you understand what is happening. All right. Can everybody see frames. Yes. I'm not sure if you see at the end of the class. So this is our original frame. You see that it is called X0, Y0. And the new one, I'm just going to show you this X1, Y1. It's rotated and the rotation is theta. So we can see that X rotated to XY, then X0 rotated to XY. For theta angle, about what axis? Where is the axis? Where is the X? This is X. That's what. Where is the pointing out the plane for both of them, right? So it means that our original frame had the z-axis for the outside and then rotated along this z for the theta. So then we can see that. It's really important. Now, we want to find the rotation matrix that causes this kind of motion. A lot of time you have rotation about the z-axis, like what? Everyday life. Or heading, we call heading angle, right? So you're going to the right. You never see me animated? I always do that. So the heading in 2D, one of your degree of freedom was that theta, the heading angle, right? So it's basically rotation about the axis of the car. So if your object is in 2D, all the rotation happens about the axis. That's why this is a very important rotation. Now, how do we find it? Does anybody know from previous classes? The what? Vector decomposition. Yes, that's one. We are going to talk about that second. All right, we're going to talk about a simpler version, and then we're going to go and talk about what you mentioned. Now, vector zero, frame zero rotated along z-axis to frame one by theta angle. One way is, do you remember when I was talking about this, I said that this XSB is to find out how much x-axis rotated with respect to the other axes, X, Y, and Z. So here we have only X and Y. So we are gonna find out this new XY, X1. How much is rotated with respect to X0 and Y0? How do we find that? So I'm trying to find X of the original, right? The initial frame, and then the new frame. I want to know what's the rotation of X1 of the new frame with respect to the old frame. So this is your initial frame. This is your new frame. How do I find this? I'm basically trying to project X1 on the two original frames. I know you know, just tell me. Yes. Yes. So when we are dealing with reference frame, the magnitude of our axis is 1 unit vector. So this means that we don't have to care about that. The only thing is the angle between them. So one way is to find the dot product. That's the second method I'm going to talk about. All right, so you two are saying the same. But if I told you X1, which comes from dot product, if you remember, dot product was what? The projection of one vector to the other one, right? So what's the projection of X1 to X0? X1 times X0 times cosine of that, right? You're projecting that one. So I'm trying to find what is this? What is this? So this becomes cosine of theta. What is this? Sine of theta. So I know the projection of X1 to the initial frame. initial axis. Now you have to do the same thing to find out where y is. So your y is y0, 1, right? Now what this is, what is this? So this is here. And then if we continue, the other one is here. What is this and what is that? Start from here. What is this? Negative cosine, right? So here, no, negative sign, negative sign, negative sign, because this is this, and then that's sign. Negative because it's on negative side. This is cosine of theta. So we have negative sine of theta in the x0 direction, cosine of theta in the y0 direction, right? Does that make sense? Everything starts from here. This is very simple. If you understand this, I promise you the first 3 weeks of this class is a breeze. Now, do you remember that to find the orientation or rotation matrix, we needed to put these next to each other? So I only have, so z-axis didn't change. So I only have x0, 1 and y0, 1. So the rotation becomes whatever x0, 1 is and whatever y0, 1 is. This is a, for now, we stay to this, and then we are in 2D. So that would make sense in 2D, and then 3D, we have a slightly different version. So all I'm doing is bringing those down here. So this is your rotation matrix along z-axis in 2D. Usually we show like the rotation subscript or along what axis? The rotation along z-axis in 2D is always this matrix, 2 by 2, because we have 2 dimensions, right? And those is always sine, cosine, negative sine, sine. And cosine. Now, if that table was 45, what would be your matrix? Or let's say it was 30. Huh? So it was sine, cosine. What if it was 90? What's cosine of 90? 1. Sine of 90. 0. Right. So you see that the matrix is 0s and 1s. So when your theta is a multiplication of pi over 2, your rotation matrix is always 0s and 1s. And if you think about the orthogonal axes, they are rotated 90 degrees on each other, right? So you can always go from here, get back to orthogonal, and why they always stay orthogonal, because they're always rotating on top of each other. Now that we know the 2D, we can expand it to 3D. Now, what if this happened around in 3D space? What would be the difference? It would be a 3 by 3. So instead of just finding x0 projected on x1 projected on x0 and y0, you had to project it also on z0, and same for everyone. That's why it becomes 3 by 3, which is this guy. You'll see this in your book, and you usually show that like whatever that value in here is where r, I think in your book is r, also r11. This just means a variable that is mixed up sine cosine. Now, there is another method to do this. Instead of projecting them, you can say that I can use, I'm going to write it here, direction cosine method, which is using the characteristic of dot product, which we basically did. That projection is dot product, right? I think that's what you were talking about. So for that, using direction cosine, x01 will be x1 dot product x0. which we did. X1 was 1 unit vector, x0 is 1 unit vector, and then you have sine cosine in it. And then you will have x1 dot y0. So projection of x1 to x0 and to y0. Your y0 1 is y1 dot x0, y1 dot y0. Then R is your x01, y01. If you put them together, R01 is going to be x1 dot x0, x1 dot y0, then y1 dot x0, y1 dot y0. Do you see a pattern here? What is happening? Look at this. The first vector in the column remains the same. It's the axis that you're trying to find where it landed. The second is always changes. It's the axis in your initial frame. Now, if it's in 3D, you're going to have x1 dot z0, y1 dot z0, and then you have z1 dot x0, z1 dot y0, z1 dot. Which is this guy. So there are two ways of doing this. One, doing the projection by hand, by look observation. The other is just following the dot product. Both of them are the same. If I ask you to use direction cosine, I want you to write this. Because what is z1 dot z0? Dot product of this. 1, 1, and sine. So it will be a matrix of sines, and we know the relation between sine and cosine of the same angle. So. Good. All right. What time is it? Yeah, 5 minutes. This is in 2D. I want you to do this. We already done it. So like try to find the. So this is the same rotation you saw, but I want you to do a rotation matrix of 3 by 3. So what is R of frame 0 going to frame 1, but for all 3 dimensions? So you have to find a 3 by 3 matrix. I'll do this on Friday again. I want you to try to use what you just learned. The sign or x0 is here, they're rotating to 1. Did you solve it? Okay, no, you have to show me your work. So you always have to show me your work. You can't say, I know what the rotation around the axis. I don't care. I need to do it. So you always have to do the math. Welcome to direction to robotics. Yes, I need to do the math. You can use direction cosine method. So you can write that 3 by 3 and then find out what are the element of the matrix, or you can use your visual strength and or you can okay. The class participation just says theta is 45. If you have this, then you can put theta is 45, and that's your class participation. Yeah, so the class participation is the same, just theta is 41. So once you have the rotation matrix, you plug in theta. So. All this for 45 minutes. So, 45. The only one we should- So, you remember my video was actually looking at real one, right? And why do you want to? So you will have this. What? Even because this is single right? I want to make sure that you have to complicated. I'll know. Bring them all out. I don't. Memorize. But we need to be able to do it. There are different consulting things. No, all of them. Right? If you go through this, that's what you do. That's what you want, But it is. correct. This is the final product.
Like,
I don't know how you do that. This is a very simple standard relation we have also on X and Y. Now, what if
so the,
you have it? Then you can use imagination and projection. You have to use the dot. I'm trying to make that one follow.
hold on. So, I didn't.
Give me a second.